you would have seen that in terms of waveform itself, when you consider real and an ideal diode, it's not much difference in terms of a performance, but the magnitude can change. So we will be assuming for the time being the diodes are ideal, but we've seen if you had to use a real diode, you would have to know the resistance and also the breakdown voltage. You can add it. So these things can be easily considered. But the first analysis you would do is good to always start with an ideal diode to know how to behave, and then you can just add these elements just to understand what to be the real behavior you would get. Okay, like I said, we won't be covering clampers. It's just there in your notes if you want to read it out of interest, but it's not for your module. So you're given your input there. So you have a series of circuits that we'll be considering. We've considered none of these. We've remember the one we just considered, the resistance was actually, actually this one we've considered already. So this is what we had. So this one here, where you have your diode and your resistor. So it is exactly the same as part B. So this one we've already done it, but it's good to try it again. This can be a bit confusing, so I would want you to develop the competence to draw the waveforms for all these cases there. Make sure you can do it. Even if it's a very simple circuit, it can tend to be a bit confusing. Yeah. Now let's try to analyze each one in turn. I'm just going to first take this into Paint. Yep, so this is your input waveform. I'm just going to clear all this first. So that's your input waveform. Now, normally what I do, I would first draw your input waveform, and then below it, I'll be drawing the output. Just draw it here in green. Yep. So the good thing is when you have your input like this, you can start putting lines on that and then deciding on some thresholds and for different regions of your waveform, what performance you would expect. Now, since we look at this circuit there, and we are assuming in this case ideal diode as mentioned here, just to know the behavior of the circuit. Yep. So we're going to replace the diode either by a short circuit in forward mode or by a open circuit in reverse mode. So just think about these two possibilities only. Then the analysis becomes simpler. Let's look at this one, the first one. So as we are doing it at the same time, you could be drawing this in your copybook, and then we can be doing it together. Yeah. Normally, class, I'll be going around and checking if you can draw it. Unfortunately, I can't do it now. So I would encourage you to make sure you are following well. If you get any problems, do let me know. I can explain again and again. There's no problem. So you are applying this waveform, what you find there, 15 volts AC. We are not giving any information on the period there, so we can't get the frequency. But if I assume, for example, this was 50 hertz, yep, if this signal was 50 hertz, you would know this is 40 milliampere and this is going to be 20 milliampere. So you can calculate very easily the time index if you knew the frequency. Yep. So this V here is what is applied at the input. So just like we did earlier, if that helps you, you can just put some labels for your nodes. So let's assume this is A here, and this is B. Okay. Now next, we assume B to be always at 0 volts. Like I've said, this is one convenient way to deal with this. You assume this was 0 volts. So in the positive half cycle, I just put that as plus. So in the positive half cycles, in the positive half cycle there, your A is positive with respect to B. In the negative half cycle, your A is negative with respect to B. We assume B to be always at 0 volts. Yep. Now next, if that is positive here, if your A is positive, look at the diode. It means you're trying to flow. If that's positive with respect to B, current is trying to flow in this direction, and the diode is reverse biased. So just like we did earlier, I would encourage you to write this down if you want. I'm just going to do that just to maybe help you in doing that. You're going to write it like this. Okay, so positive half cycle. What do we get? Let's document it. So positive half cycle, we look at the circuit, we find A is more positive, so the diode D would tend to be, so T will be reverse biased. Yep, so this is what we can conclude. If that's not clear, let me know, because I'm following up with what I've said earlier about biasing. So if you try to flow a current in the opposite direction where you have the bar, definitely the diode is reverse biased. And what you would do now, if it is reverse bias, you would simply replace this by an open circuit. Reverse bias means no current is flowing. This is the situation. The question for you now, if your diode is reverse bias, that situation, what V0 would you measure here? Think well about it. What V0 do you think we're going to measure if that is an open circuit there. Any suggestions? Can you just put your answers in the chat? Let me just see what are you putting. Can you just suggest what are you going to measure at V node if you are in this situation? What would V node be? If you want to take some examples, let's say we are talking here of a positive half cycle. Let's say we are applying 15 volts. So 15 volts is being applied there. So A is 15 volts. What would V node be? So can you send some questions in the chat and let me see what do you think V node is going to be? Okay. Yep. So most of you have said 15 volts till now. So those who are not sure, what's the correct answer? Yep. Because let me explain the thinking behind it. If you don't have any current flowing, you don't have any drop across the resistor because the resistor needs to have current to have a drop. So the moment there's no drop there, the full supply needs to appear across the open circuit. If you were to connect in a voltmeter here, you would simply measure the supply. That's right. So it means in this analysis, it's important for us to demarcate the positive and the negative cycle. So how we do that? We simply put some lines. Later, the lines may not be always at where we are drawing it now. It may be at some other places. But for this particular case, we find the positive and negative are the determinant thresholds for changes in your output waveform. We put it like this. Let's draw for all the cycles. So we've concluded here for the positive half cycle here, we're going to measure actually the waveform. So in that positive side there, we are showing idle diodes as a no drop. We're simply going to measure this one itself. So we just bring it down. This is what we're going to measure. Let's try to, it's transparent. Okay. Yeah, so this is what we expect. Let me just do that again. Okay, this is what you expect to get in the positive half cycle. Now let's look for the negative half cycle now. So let me just write it again. I expect you to write this in your copybook. So in the negative half cycle, okay, what would your diode D be? Let's just take a case. So in that case, if that's 0 here, your A is going to be negative because it's a negative half cycle. So now you're trying to flow current from, this is 0, this is negative. You're trying to flow current from 0 to negative. So your diode is forward biased. So D is forward biased. So when you're in your negative half cycle, your diode is forward biased. For forward bias, we've said already, you would replace this by a short circuit. So this is the situation. Yep. So in the negative half cycle there, we've concluded that A is negative, 0 is higher than negative, so current will start flowing in the opposite direction like this, and this diode is forward bias. Forward bias means you can short circuit it. This is the equivalent if you want circuit for an ideal diode in forward bias mode. Yep. So now the circuit becomes very simple. What's going to be V node? V node is the voltage drop you have across a short circuit. The voltage drop across the short circuit is always 0 because the resistance is 0. So the full, when current is flowing here, the full drop that you have, the voltage applied would appear across R. There will be no drop across V node simply because the short circuit resistance is 0. V is go to IR, R is 0, so your voltage becomes 0. So in this region there, you would measure 0 volts. And similarly, you just have to copy this across. It's going to repeat itself. So once you get the analysis for 2 cycles, as you can see, it's just going to repeat. This is what's going to happen. More or less. Yep. So this is the output waveform, and you find that we get exactly the same answer we got for the earlier circuit where the diode was here, but this one was in the opposite sense. But the waveform you're getting is exactly the same. So this is also doing half wave rectification and is keeping up all your positive half cycles. Yep. So I give you just some time, just draw that in your copybook if you want. This is important, and then you can do a similar analysis on your own when you get the notes. Yep. So just give you a few minutes just to try to do that. So again, this circuit is a half-wave rectifier because we are keeping half of the positive cycles only, half of the negative cycles are being thrown away in a way. Okay, let's continue. If you need more time, just let me know. But as I'm explaining, you can always be writing down. I would encourage you to have your copybook next to you and to be taking down notes. Now let's consider one more, and then I'll be leaving that for you to continue. I won't be discussing all of them. So I expect you to be able to do this one and this one on your own. This one we've done it already, but I would encourage you to do it again. And you can do this one as well. So very similar circuits. And this one as well. Part D also you should be able to do because these are very similar ones. I would like to do one of these two for you now. Yep, I want to do one of these two. And in the analysis that follows, they actually give a detailed explanation of one of them. So let me see which one is this. This is this one here. Yep, it is this one here. So I will do that. I will explain that again to you, and then you can go through that where I give a detailed explanation of what do we get, and then you are given actually second example. So it's quite comprehensive there. Yep. And then I've given you some examples to try. Yep. So let's do one of them in detail, and then I would expect you to then read in the notes, because I do admit it can be a bit confusing, this one. So why I want to go into detail of one of them for you. Yep. So let's take this one. So again, these four top there, you should be able to try it. If you still get problems in the next class, you can ask me. I will explain it again. Yeah. Again, that's all to encourage you to do self-learning and to be able to apply the principles on your own, to appreciate the analysis and be able to have a good grounding in the fundamental principles. I suppose make sure you're not learning this waveform by heart, because it doesn't work like that. So it's impossible to learn this by heart. And remember, you won't be getting the same circuit for exams, for tests, and so on. You need to know how to analyze the circuits. That's very important. So I'm just going to copy again the input waveform. So it's always typical to just draw the input waveform as you're seeing, and then to sketch the output waveform just below it. It's easier to do it that way. Now, in this case, you will find that the threshold is not necessarily at exactly the half cycles. It's going to be a bit different. So follow here this one carefully. It can be a bit confusing. Yeah. So what I'm going to do here, I'm going to follow exactly the same method I've said earlier. Let's write our AB. You're going to see now how convenient it is to use that AB method. Yep. So let's again assume here we have A on top here. Put it black. You still have your A here, and you still have a B here. You have your AB, and as usual, let's assume this is always 0 volts. So your B is grounded at 0 volts. It's a nice convention to use. So as we've said earlier, you have your positive cycles there, and you have your negative cycles. Now, what I want you to look at now, if you see 0 volts, if you start moving from 0 volts and then you start moving up, what voltage? I'm going to put a third point now because you have this battery there. Let me put a point C here. Try to think what would be the potential at point C. Just put more load in. I did give you some indication. Remember when we did the basics, I did mention that when you move across batteries, what should you do? So according to you, what is the potential at C? If you assume B to be at 0 volts, what potential will you have at C? Can you send me some answers in the chat? Let me see if you get this right. What potential will you see at C if B were at 0 volts? And this is 10 volts battery here. Let me see some answers. So there's no problem if you get it wrong. Just keep trying. I would know what are the problems and I can help you. So just try to suggest something. Don't be afraid.
10 volts.
Is it plus 10 or minus 10? 10 volts the magnitude, that's fine.
Plus 10.
Okay, some of you are saying plus 10. So I could have done a Mentimeter here, maybe to encourage you to vote. You know, maybe you have used Mentimeter. So is it plus 10 or minus 10? That's the question. It's going to be 10. Is it plus 10 or minus 10?
Minus 10.
I'm saying minus 10. Yeah, I can say minus 10, minus 10. Yep. So let me explain that. What should it be? if you look at the, so how to solve that? If you look at the polarity of the batteries, so this is plus there, this is a plus, we know the longer plate is plus, and this one is minus. So when you move from 0 and you go across the battery, you're going in the direction of reducing potential. So when you go from this point to point C, you are going in the direction where the potential is reducing because you're going from plus to minus. This is why point C will be at minus 10 volts. Yep. So this is going to be at minus 10 volts. If your battery was connected the other way around, yeah, if I had reversed the polarity, so this was minus and plus on top, means the smaller line will be down and the longer line on top. Then as you move from B to C, you're going to move from negative potential to positive potential, then point C would have in plus 10 volts. So I hope it is clear. When you get other examples now similar like this, you would need to put the polarity right. Now it means why I've come to this stage here minus 10 volts, because this is the polarity which your diode would see. Okay, so as you can see clearly here, it's not the ground which is going to be a threshold, it's going to be minus 10. So on your diagram, you would have a line somewhere. If I draw that in range, so you would have a line there which is at minus 10, because minus 10 is going to be an important voltage to decide if the diode is forward biased or is it reverse biased. Now let's write it down as we did earlier. Now look at VG. Yep. So when this diode D is forward biased, that's a question now for you. So if I just write it here, when is D forward biased according to you? Knowing that one side is minus 10. So this diode is forward biased only when VG, which is there, is connected on this side, on the positive side, only when VG is more than minus 10. Yep. So if let's say, let's take some examples if you want, if you just put some there, if you get problems to understand this. If I put a voltage there of minus 10 volts itself, if you are minus 10 here, minus 10, the diode is not conducting because there's no voltage drop across it. If I put minus 15 volts, 15 volts, if you have 15 volts on this side, this is minus 10. You can clearly see here the diode is reverse biased because this is more positive, and this one current will try to flow in this direction, means moving up, but diode is reverse biased. If I put a voltage of minus 5 volts here, you can see now the current is trying to flow from minus 5 to minus 10, so this is forward biased. So what is the threshold to decide when the diode is forward biased or reverse biased? Is minus 10 volts. So the diode is forward biased when your applied voltage VG is actually greater than minus 10 volts. Greater in the proper sense. It has to be minus 9, or it has to be minus 8, it has to be minus, and so on. So the moment your VG is greater than minus 10, if it is positive, that's fine. So all this region here, which is above minus 10, the diode is forward biased. Automatically, we say the diode is reversed biased when your VG is less than minus 10 volts. I've taken some examples already for you. If you place minus 15 volts there, which is less than minus 10, or just take minus 11 volts if you want, you find that the current will start trying to flow in this direction. So the diode becomes reverse biased. If you take any voltage here, which is more than minus 10, let's take minus 9. If you put minus 9 there, the current is trying to flow down from minus 9 to minus 10. The diode is forward biased. So these two are correct. Now, next step, once you've done that, just like I've done, you're going to now, you're just going to short circuit or open circuit the diode. So if you take the first case there, the diode is forward biased for voltages more than minus 10. Forward bias means you're going to replace the diode by a short circuit. So this is your short circuit. So yeah. So this is for this case there. And where is VG more than minus 10? It's this segment there. This one up to here. So it means on your graph there, you have to drop some lines which are at minus 10, so intersection. So these are important points. This one here. So this is the important point. This one as well. Because from these points, you find a change in behavior of the diode. The diode is going to shift from being a short circuit to one being an open circuit. So how we draw the graph now, look at how V naught is measured. That's very important. V naught is not measured only across the diode, it's measured across the whole point there. That's important. So you will basically measure minus 10 volts. When this is short circuited, you're simply measuring minus 10 volts. You're measuring the battery as well. Yep. So in this segment there, it means from, I have to draw this line a bit more down. So I hope you're sketching at the same time in your copybook. Yep. So what are we saying here? If your diode is forward biased, it's because it is above minus 10 volts. In that segment, you will be measuring minus 10 volts. It's not zero, because if my V0 was measured only across the diode, you would get zero. But you're measuring it across the whole, including the battery, as you can see here. So it's important to know where are you measuring V0. So in that segment there, you are simply measuring minus 10. In this whole region there, you're measuring minus 10. Yeah. So if you assume this is minus 10, yeah. Okay, and similarly, if you continue here, this segment there where you go above minus 10 is again minus 10. So the moment you're above minus 10, you are measuring minus 10 itself. So I'm just going to extrapolate up this segment there. All this is minus 10 and all this will be minus 10. Okay, now next, the remaining part is to know when you are in reverse bias mode, means when you are less than minus 10, what are you actually measuring? Yep. So now when you are below minus 10 volts, we are saying the diode is reverse bias. Reverse bias means you can simply open circuit this now. Yeah, this is a situation you're open circuiting, no current is flowing. The question for you now, what is V0? So you're measuring V0 across these two terminals there. Any suggestion? What would V0 be when your diode is reverse biased? Remember, your V0 is being measured. If I just put some nodes there, so this is measured from here to here. This is what V0. So if you can imagine putting a voltmeter here. So if you put a voltmeter here, remember no current is flowing in the circuit because this is open there. Yep. So you don't have any drop across your resistor. You're simply measuring your supply. Can you see from here to here? You're simply measuring your supply because you're not taking that drop here. If your voltage was measured at this point, you would have to take VG minus 10. Can you see? You would have subtracted minus 10 from your supply. Yep. But you're not doing that because you're measuring it from here to here, which is nothing but VG itself. So what is VG itself in that segment? That's quite straightforward. You will just pick that up. That is your VG. So you'll be measuring that here. This is what you will get. So in the negative half cycle, you will simply measure the supply, because this is the way you're actually measuring your output is from here to here, and this is nothing but the supply. And since you are open here, yep, so no current is flowing, so no drop across R. So this is what you're measuring, VG. Yep. So if you look back now, to give you a few minutes again, if you want to copy this. Now, if this is not very clear now because you're doing the first time, this is what in your notes I've described this in detail. All the steps, all the different states I've shown there is all detailed very well in your notes. I would encourage you to read that. You have few more examples I've given for other circuits, and then I've also introduced some examples. So I would leave that to you because I know this can be quite confusing the first time you're doing it, but I hope if you just read more on that and you get a technique I've shown to you. There are other techniques you can use, but I think this technique works well. I've seen students understand this very well. This method of using 0 volts there and then writing this at minus 10 and then starting to see when a diode is forward biased, when it's reverse biased, and then from there you will present your diode as a short circuit for forward mode and a open circuit for reverse mode, and then seeing what are you getting at the out. This should give you the answer every time. Okay, so I'm shifting here. If you look now at, so we've just done this one. Yep, if you do this one now, you find that if that is 0, this is going to be at plus 10 there. And then you can do a similar analysis. So I've explained this one in detail here. I would encourage you to read that and to get these answers, which I've shown to you already. And the second example is also given there, but you can see that the battery now is here. So you are going to fix this one at 0, and then you see if that's VG, then you're going to get VG plus 10 here, and then so all the analysis is given there. I would encourage you to look at that. Here it's a bit different because your applied voltage is 20, but you are able to go beyond 20 because the battery here is, this battery here is increasing your supply voltage by 10 volts. This is why you're 20 here, but you're able to go to 30. Yep, so I would encourage you to read that. And once this is clear, these two, you can give a try for this one and this